with the backplane and the power supply all done, it's time we actually go into the building a computer part. And to do this, we first have to decide what signal we want to have where on our backplane. Because of the way I designed this, one thing already determined, and that is ground is line 1 and VCC over here is line 2. And now I can basically decide what we want to do. So I'll put reset on line 3 and clock. Where's the clock pin? Over there. On pin 4, and then we'll have all the address buses, all the address pins. So this is 5. And this is 20 over here. And then we'll put all the data lines, which means this is 21. And the last data line, which is right next to it, is 28. And from there, I'll just put all those system control things, I'll just put them down in order. Because let's say this is 22, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, and that's our 40 pin bus. I might, especially those control lines here, I might shuffle them around a little bit. Example, I don't think I'll need bus request and bus acknowledge. Those are mainly used for DMA. And I don't plan on using DMA at the moment, so I might delete those later on and not have them on the bus, but I'll decide that when I build the processor card. Yeah. So with that decided, I think it's time we think about what we want to have on our first card for this Z80 computer. And I think the best thing would be to, for the first card, to put a couple of utilities and also facilities for the front panel on it. And that means I want to have clock on this. The clock generation circuit. So just put a block diagram here. And just write clock. And the bus is down here. I'll just have the clock line coming out here, disconnected to ground. And I also want some reset circuitry on here. And I want both automatic and manual reset. So that means I want the reset line that's also here on the bus. I want this to be low when the computer starts up, and after the power supply stabilizes, I want this to go high and basically reset everything until everything is in a known stable condition. But then I also want to have a switch here. I'll just pull this down to ground here. A switch for basically manual reset. That if we fuck anything up, you can pull down this switch and everything will be fine. And then I also want single stepping circuitry on here. So I'll just write single step, and also powered, also has a ground line attached to it. And this now has two switches. One that decides run and step. It's basically if it's on run, it's free running, and if it's on step, then we can single step the CPU. And this is immensely helpful for debugging because it will in single stepping mode, it will execute a single instruction and then go into a wait state. And that's great for debugging. And then also we want another switch that it's basically a step switch. Every time we use this, it will step. And you can do this with two lines on the Z80. One is the wait line. So just make the CPU wait. And the other one is called M1. And M1 is, I think, machine instruction 1, which is basically this does something every time the Z80 fetches an instruction. So at the beginning of each cycle, this will go high or low. I don't know what it does exactly, but we'll find out very shortly. And then I'll just draw this as a bus here. Bus. I want this card, because this is not all that much circuitry for a card. I want this to have basically another connector on here that brings out the address, so A0 to A15, and the data lines D0 to D7. Brings this out to a connector so I can connect it up to a front panel later on, so I can have some blinking lights. That would be great. So this is just front panel. Connector. And what we need to do on the front panel is we need to buffer all of those, because we don't want the LEDs to draw current from the processor or anything. You can't pull 10 milliamps off the address line of the processor. That would be very bad, and it's a sure way to get yourself into trouble. So we have to have the front panel buffered later on. So this will go to the front panel, which will also have VCC and ground attached to it. So I'll think about how to implement this for a minute, and then I'll be back here very shortly. The first thing I'll design for this card is the clock generation circuit, and we're going to use a very, very classic circuit, and that is basically based on an inverter chip, 7404. and the inverters are basically just coupled end to end. 3 of them go like this. This is A, B, and C. And what we're going to do then is to connect this to a resistor that provides a little bit of positive feedback. Then you're going to connect this to another resistor that connects to here, and across all of that we're going to put a crystal like this. In my case, I have an 8 megahertz crystal in here, although on the actual card I will put a little socket on there, a very tiny socket, so it doesn't interfere much with the crystal, because capacitance can be a problem in circuits like that. But I want to actually change that later on. At least I want to be able to change it, because 8 megahertz makes for a problematic serial clock. So something like I think 7.12 something would be better, or half of that. But I don't have that crystal at the moment, so I'm going to put an 8 megahertz in the socket in. And we derive our actual clock frequency from here. We're going to pull this up. These are, by the way, 270 ohms. 270 ohms. And this is 330. And the reason for this is that TTL outputs can sync no, that doesn't make a lot of sense. I don't know what this resistor is for, but it's in all of the diagrams that you find on the internet. So I have to think about this for a second. So I thought about this, and the only thing I can think of is that this TTL gate won't actually go up to exactly 5 volts, the supply rail. Here, yeah, it's on all of them, like this. So this actually will probably allow some current to flow down here and actually pop it up to 5 volts, although I'm not sure about this. So I built this circuit up on a breadboard, which is nothing you should do to clock circuits, because all the extra capacitance, yada yada. Don't build RF circuits on breadboards, but for this case it actually works. To verify that, I also built it up on a little prototyping board, and it works just the same. It has an 8 megahertz crystal in here and 7404. So a couple extra things I did to this to actually improve the signal this generates, and it's still not perfect. I'll put in the waveform up here, so you can actually take a look at it. And the issue with that is that it's actually well, it's generating a square wave and it's oscillating, but it is also there's a sort of sine wave that's superimposed on it, so that is an issue with that. So things I did to improve the clock is I put a decoupling cap of, this is actually the one that I took the measurements on. Although there was very little difference between the large decoupling cap and the 22 nano here that I put in. I took some measurements of this, and I took some measurements of this, and the oscillation is actually a little worse on this, as you would expect, but it's not great on this either. And yeah, that's just about it. What I also did, not on this one, but on that one up here, and that also improves it just a little bit, is I took all the unused gates. Just going to draw a couple inverters here. And I tied them all to VCC with a resistor of 270 ohms, and that actually improves it a little, because those inverters are now not oscillating around and causing interference with this. You can see the clock is still not perfect, but I think it will do, and I'll design this in, and we'll just hope it works. Also, we're going to have to respin the clock generation card, but I don't think so. I think this will work just fine. The second part of this board that we're going to design is the reset circuit, and I want something that, as I said it before, that does automatic reset on power on, and that also does manual reset if you press a button, if something has gone wrong. And how we're going to do that is with a Schmidt trigger. Basically, we've got a switch here, a bit of a weird switch, but and now we've got a diode here. This is also, this circuit is directly from the Build Your Own Z80-Computer book. But it works fantastically, so there's no need to reinvent the wheel. And here we've got our Schmidt trigger inverter. And just to follow this up, we've got another, almost Schmidt trigger inverter here. Those have always been really hard to draw. And this is just connected to power. This goes in here, and this goes out to our reset line. And how this works is when you first power on the circuit, this is, by the way, this is 10K. Current flows through this resistor, charges up this capacitor, and once it's over a certain point, this will be high, this will go low, therefore this will go high, and actually start everything up, because reset is active low. And then same thing, if you press this button, capacitor discharges, and this goes low, therefore this goes high, therefore this goes low, everything is reset. And then it starts up again in a very controlled fashion. And just to demonstrate this, I put this on a little breadboard, and also have this connected to the oscilloscope. And I'll actually put some pictures up there. But for a better visual impression, I also have a LED here that shows what's going on. So at the moment, reset line is high. And now I'll just do what a switch would do. I'll connect this to ground. Bang. And low. And high. And this happens in a very controllable fashion. The thing is, in the actual circuit, this capacitor will be much smaller, and so this delay will be Also a lot shorter, but just to demonstrate this here, I'll put this larger capacitor in. If you put in the small capacitor that I'm going to have in the circuit, it's very hard to see that there is any delay, but there is. You can actually barely see it. Yeah. So this is the schematic for what's going to be on this first board. Going to have our backplane connector down here. This just supplies ground and VCC, and then I'll basically duplicate all the lines from here to another connector that's going to sit on the board, and this is going to go off to the front panel, so we can just get all the data lines and everything for the LEDs on the front panel. And then we also have the clock generator previously discussed here. That's going to provide the main clock of a couple of megahertz, and reset circuitry over here that just takes VCC. There's both take VCC and ground from the backplane. Keep this in focus. And put the and they will put the reset and the clock down here. And instead of a single stepping circuitry, I just have a very slow running clock. This is an NE556, double NE555 basically. One of them creating a slower clock of about 1 Hertz. And this is just going off to a relay, and that relay is switched over this connector. That also provides the switch for the manual reset. And I've got the second 555 hooked up as a monostable, basically a one-shot. And this is supposed to trigger the wait line, so you can, when you're on the slow clock, you can just pull the wait line down on the Z80, so you can stop at the current instruction. But this is not working so great. So I've got the little prototype system here, breadboarded up with the fast clock over here. This is not even connected at the moment. The reset circuitry over here, and this resets just fine. And the fast running clock over here, and the one shot over here. This is implemented in 2 555s. And at the moment, I just have a pull-up resistor on here and a switch to ground, and this actually works. Oh, there's my multimeter. This works surprisingly well. I'll just stop it, and this doesn't have any debouncing circuitry, but it seems to work just about fine. Yeah, you can reset it again. It starts counting again. The issue if I connect a one-shot and this hooks up to pin 2, and then this output hooks up to here, is that it doesn't work. And if I pull out this resistor here and just reset it again, it will make the processor do weird things. It's flashing on the address lines up there, and it will not work reliably for some reason or other. So I think I'll just go with, either I've made a mistake in this prototyping setup over here, which is possible, or if not, this just isn't working very well. And if that should be the case, I'll try this on the final board. I'll just put the circuitry on, and I'll just test this here again. Yeah, it does all sorts of weirdness, and it doesn't really. I think before I accidentally had it in the wrong slot here. I think I was actually pulling on the bus request line, but if you activate this now, this makes it go completely bonkers. So I think if this shouldn't, I'll put the circuitry on the board. I already have it designed. But if it shouldn't work, in the layout I built this in a way that you could just not put in a jumper wire, and then this circuitry is disconnected. I would basically just sit there doing nothing, and then I can just, instead of the circuitry, I can just put in a switch like this with a pull-up. And this seems, even with no debouncing, to work much more reliable, which is odd enough. So yeah, that's my little prototyping setup here. Now let's get that out of the way. This is the board for this first card. See over here, it's got the backplane coming in and then everything going up to a connector. And it's got the 3 chips up here. I'm just going to populate that now. Well, drill the holes and populate it. The thing is, I'm still missing the angle headers, so I can't actually put this on the backplane yet. But I'll populate it and we'll test it and we'll see how it works. I've got this board all assembled now, and it works perfectly fine. The thing I haven't populated yet is this expander header down here, because I'm still waiting for the parts. What I did with this thing, where I was actually supposed to have a right angle header, I just took a straight one and just soldered it down here to all those test points, and that actually works fine. I think it's equally rigid, but yeah. So we've got the 3 chips here and the interface for the switches up here, also a relay that switches in between clock sources. This is the first board that's actually ready. So I think the next thing I'll design is either a processor board or actually the front panel board. I'm not sure about that yet, but I think I might do the processor board first.